Hi everyone, I'm the Babywearing Math Teacher, and today we're going to look at how to solve and graph inequalities. So the first thing I want to look at is an equation. We're all familiar with equations and we all know how to solve those in our sleep. So if we're wanting to solve this equation, we want to isolate the variable using inverse operations. So the opposite of plus 4 is to subtract 4. Here the 4's cancel, and my solution is n equals 11. So in an equation, you get one exact, precise solution. That number is the only number that satisfies it. And in an inequality, we're going to actually get infinite solutions with just one parameter that we're going to look at. So if we look at an inequality, we're solving it initially the exact same way that we would an equation. So if I have y minus 8 is greater than 10, the greater than sign just kind of replaces the equal sign, and we're still isolating our variable across that sign. So instead of subtract 8, we want to add 8 to both sides. Here the 8's will cancel. I get y is greater than 18. So now instead of 18 being an exact, precise solution, I know that I have infinite solutions that are bigger than 18. So 20 would be a solution, 25 would be a solution, 125 would be a solution, and so on. So anything greater than 18. But 18 itself is not a solution. So as I graph this, I want to put an open dot at 18. So on the number line, I put an open dot, meaning that 18 itself is not a solution, but everything after 18, such as 18 and 100th, 18 and 1,000th, all those would be solutions. So I want to shade all the way from the 18 up. To test and to check my solution, I want to pick a number where I shaded. So for example, 20. If I plug 20 into the original inequality, my inequality should be true. So if I plug in 20 minus 8 is greater than 10, 20 minus 8 is 12, and it is true that 12 is greater than 10. So any values bigger than 18 will satisfy my inequality. Let's look at one other example. So here I have a greater than or equal to sign, and that's going to change it just a little bit when we graph. So I'm going to isolate my variable by subtracting 4 from both sides. So now x is greater than or equal to negative 21. Now when I graph this one is going to be different in the sense that negative 21 is a solution. So instead of that open dot, I'm going to shade my dot in at negative 21. And then all values greater than negative 21, so negative 20, negative 19, up to 0, and all positive values will work. So I'm going to shade in this direction. So then I want to pick a value. So I like to pick something that's nice and easy. If I keep going and going, I'm going to go well past, but I'm going to get to 0. And if I plug in 0, that's a nice easy value to check. So 0 plus 4 is greater than or equal to negative 17. Well, 0 plus 4 is 4, and 4 is in fact greater than or equal to negative 17. Now when we have that little line underneath, that means it could be the value in our solution, so I can also test the negative 21. So negative 21 plus 4 is greater than or equal to negative 17, and when I add that, I do get exactly negative 17. But this solution does satisfy the equation, or the inequality, because it does have that or equal to. Next thing we want to look at are two-step inequalities. In a two-step inequality, you will likely be multiplying or dividing to get your answer. So here we're going to look at 3x minus 6 is less than negative 18. Alright, so what I want to do is save my variable for last and get rid of minus 6. So I'm going to add 6 to both sides. So here the 6's will cancel. I'm left with 3x is less than negative 12. To isolate my variable, I want to do the opposite of 3 times x, so I'm going to divide by 3. The 3's will cancel. Now I have x is less than negative 4. And when I graph this, I'm going to have all my values smaller than -4 that will work. So all these values will work, but -4 itself will not work because x must be less than -4. So I use that open dot to say 4 is not a solution, but everything just left of -4 is a solution. And then I can check my answer by picking a value somewhere to the left of -4, so maybe -6. So I take my original inequality, 3, and multiply times -6 minus 6 is less than -18. If I solve this, I'm going to get -18 minus 6 is less than -18, and then I'm going to get -24 is less than -18. And that is true. As long as my inequality is true, then I have a solution for it. All right, one more, and this is the major point where inequalities differ greatly from equations. So if I solve 5 minus 2n is less than or equal to 11. Again, I want to save my variable for last and get rid of the 5. So the 5 is positive here. To undo it, I'm going to subtract the 5. It's going to be negative. All right, so bring down the -2n is less than or equal to 6. Okay, to isolate my variable at this point, I need to divide both sides by -2. And with inequalities, to keep them true, anytime you multiply or divide both sides by a negative, your inequality is going to flip. So instead of reading less than or equal to, it's going to read greater than or equal to. And then I'm going to go ahead and divide these values. That will keep your inequality true. And the way that you can really make sure that you've done that correctly is by graphing. So I'm going to draw my number line. And I want -3 in there. And it could be greater than or equal to, so I'm going to use the closed dot to indicate that -3 is a solution. And I'm going to shade toward all the numbers that are getting bigger than -3. And then of course I want to test, so maybe I'll plug in -1. So to my original inequality, 5 minus 2 times -1 is less than or equal to 11. So the first thing I want to do is multiply -2 times -1. That's going to give me +2. And 5 plus 2 is 7. And it is true that 7 is less than or equal to 11. Now, as long as you're checking your answer, you're going to most likely be shading in the correct direction. If I hadn't flipped my inequality and I tested an answer, my inequality would not be true and I would need to go back and check my work. So that's how to solve and graph inequalities, brought to you by the Baby Wearing Math Teacher, because math is so